All right, in this video we're going to be looking at what's called a geometric sequence. Now remember, you might recognize the term sequence because we have seen that before. It's back in chapter 1 when we learned about arithmetic sequences. Where there is a sequence of numbers with a constant difference, we call that constant difference d. So an example of an arithmetic sequence is like the one shown here where we have 7, 10, 13, and 16, and it keeps going. If you notice that in that scenario, our first term is 7, and our constant difference is 3. And so remember, in that situation, we had recursive formulas and explicit formulas, or a recursive formula and an explicit formula that we could use to represent that sequence. And then, especially with the explicit formula, we could use in that formula to find specific values in that sequence down the line. And also, if we were to graph those, it would be a linear function. And that's why it's back in chapter 1. Well, in this lesson, we're going to be looking at geometric sequences. And these sequences follow a different shape of a graph, one that we've talked about this chapter. In fact, it's an exponential function. Well, what is a geometric sequence? Well, it's a sequence, but this time instead of adding the same amount each time, there's going to be what's called a constant ratio, or we're multiplying the same value from one term to the next. And that constant ratio, or that common ratio is another name for it, is we use the letter R. So whenever we look at different formulas here, the letter R represents that common ratio. So here's a little hint. To find the value of R, what you're going to do is you're going to pick any term in the sequence, just not the first one, and divide by the value before it, and that'll give you the value of R. So for example, let's look at this one. Now sometimes it's really easy to find that value R, but I'll just again show you how to illustrate how to use that trick. But here we have 7, 14, 28, 56. That might be pretty simple to see that we're just multiplying by 2 each time. But if that wasn't as simple, we could pick that number 14, divide by the number before it, 7, and you'd get 2. Or if you wanted to pick 56 and divide by 28, you'd also get 2. So the common ratio here would be R. All right. So with that sequence, we could represent it using a recursive formula. So down here, it gives us that recursive formula. So some parts to that recursive formula to be aware of is the top row. Just like with the arithmetic sequence, the top row identifies with the value of the first term. And then off to the right there, those things are just meant to make it clear what those numbers to the left are referring to. So to the right there, n equals 1 is just stating the fact that to the left there, that is in fact the first term, the value of the first term. And then in the second row, we're going to take whatever the common ratio is and multiply that times the expression g sub n minus 1. So in this formula, the only things that are going to be replaced with numbers are these two pieces. That g sub n minus 1 will always be there because that g sub n minus 1 refers to the phrase previous term. We just don't want to write the phrase previous term, so we just use that g sub n minus 1 to represent that. But what I highlighted there is the only pieces that are going to get replaced with numbers. And again, off to the right, that n is greater than 1. It just states the fact that we're using that line for any terms after the first term. All right, so let's write a recursive formula for that example 1, for the sequence we see in example 1 there. So 7, 14, 28, 56, and so on. So our recursive formula, we could write it like this. So our first term is 7, and we could even say that that's the first term. And then, again, we found that we're multiplying by 2 each time. Okay, so our common ratio is 2. So we would take 2 times g sub n minus 1. And again, that's for after the first term is when we use that expression. All right. I want you guys to write a recursive formula for this geometric sequence. It starts at 248 and then goes down to 124 and then goes down to 62 and then gets down to 31 and so on. Now remember, our R is what we're multiplying by each time, not what we're dividing by. So I want you to take a minute and think, okay, what are we multiplying by? And it could be a fraction, or you could even use a decimal there. So go ahead, give that one a thought. Pause the video and hit play when you're ready to check to see if you did it correctly. All right, well, everything on this is pretty obvious except for what's our value for R. So like I was saying, you're not dividing by 2. I mean, technically, yes, you are dividing by 2, but our ratio, or our R value, our common ratio is supposed to be, what are you multiplying by each time? So if you were to use that trick and take 124 divided by 248, you get 0.5. Or 62 divided by 124, you get 0.5. Or 31 divided by 62 would give you 0.5. Or we recognize 0.5 as being 1/2. So again, you could use r being a decimal or a fraction, but 1/2 would be our value, would be our common ratio, not 2. All right, so not only did we have a recursive formula, but we also have an explicit formula. So same thing, g sub 1 still represents your first term, and r represents your common ratio. And again, those are going to be the numbers that we're going to plug in here. N is going to be a variable, so n is referring to whatever term number. So if we do know what term we're looking for, that's what we'd put in for n. But otherwise, if we just want an explicit formula, we would just leave it as n, or you could use x. So let's write an explicit formula for that sequence in example 1. So if you remember, the first term in example 1 was 7, and our common ratio was 2. So we'd have to the n minus 1 power. By the way, that n minus 1 power only applies to the 2. It doesn't apply to the 7. So do not try to simplify this. Do not write this down as 14 to the n minus 1 power. Order of operation, the reason why is because order of operations tells us we can't multiply until we've taken care of exponents. And since I can't do anything with this exponent, since it's just an n, we would leave it as 7 times 2, the n minus 1 power. All right, why don't you guys do the same thing now for that sequence that we talked about earlier, the 248, 124, 62, and 31, the one that we just did a recursive formula for. I want you guys to write an explicit formula for that sequence. So pause the video and hit play when you're ready to check your answer. All right, so hopefully you got this. So the first term is 248. Common ratio is 1/2, and then our exponent again would be n minus 1, and we would leave it just like that. Now let's stop for a second and talk about the graphs of these. Remember I said earlier that an arithmetic sequence always follows a graph of a linear function. So if you notice, these would be what we talked about in this chapter as exponential functions, where the one in purple, the one that we did for example 1, that would represent exponential growth, where our y-intercept would be at 7, and it would look like that. Where this graph would be exponential decay with the y-intercept at 248, and would be going down from left to right. So that's the shape of these graphs. They are going to be exponential functions. So that's why we're talking about these now, and we didn't talk about geometric sequences earlier back in chapter 1. All right, well, let's look at some story problems where these would apply. So here it says a ball is dropped from a building, and after its first bounce, it bounced up 75 feet. If after each bounce, the ball bounces 80% of its previous height, how high is the ball after bouncing 12 times? All right, so after its first bounce, so this would be the first term, would be 75. If after each bounce, the ball bounces 80% of its previous height, that means we would multiply, we would change that 80% to be a decimal, and so our common ratio would be 0.8. So every single time would be 80% of its previous height. So we would just use this information, and this is saying that n would equal 12, because we're trying to figure out how high is the ball after bouncing 12 times. So we start with that first term of 75. Our common ratio is 0.8. Technically, our formula would be n minus 1 would be an exponent, but now I know what my value for n, because we're trying to figure out how high would the ball be after 12 bounces. So you would put 12 in there for n. And when you do that, you can just do that on your calculator. I'll have you practice one in a second. You can just type that whole thing in your calculator all at once. When you do that, you get 6.4, and this would be measured in feet. All right, now let's answer this one. It says, how many bounces would it take for the ball to reach a height of 1 foot? Okay, so now we're trying to find out what is n. But we know that the total height would be, or the ending height is going to be 1 foot. Actually, I'm going to do it like this. Okay, so the ending height is going to be 1 foot. We want to figure out what's n. So this goes back to what we talked about in this chapter. We want to get the base by itself. So I'm going to divide both sides by 75. So when I do that, I would get 0.8 to the n minus power. 1 divided by 75 would give us 0.0133. And guess what? This is an exponential equation. So the only way to solve this would be to use logarithms. So I'm going to take the log of both sides. I'm going to do that on this one here. So if I take the log of both sides, remember that exponent I can write out in front here. So n minus 1 times the log of 0.8 equals a log of 0.0133. So to solve for n, we would divide both sides by a log of 0.8 for right now. So we'd have log of 0.0133 divided by the log of 0.8. Again, that's just a common log, so you can use your scientific calculator. It doesn't matter what calculator you use then if you do it this way. When you do that, you get 19.4 on the right, but we have to add 1 to that, so you get, well, this isn't in feet, this is bounces, so we'd say about 20.4 bounces, or you could say 20 bounces. All right, so there you go. So I want you guys to do the same thing now to this problem. So it's the same thing in 2 different parts. So the first part, you know the value for n, and the second one, you're trying to figure out the value for n. But in this scenario, it says a particular bacteria will triple every hour. So it means it's multiplying by 3 every hour. If a petri dish is observed to have 62 of the bacteria at the start of a study, how many bacteria are present after 6 hours? And then I want to figure out how many hours would it take for the bacteria to grow to 1 million bacteria. All right. So why don't you guys go ahead and pause the video and work on both these parts and hit play when you're ready to check to see if you have both parts done correctly. Yeah, you did. So in the first part, you should have gotten 15,066 bacteria after only 6 hours. So again, if it starts with 62 and if it triples every hour, it's going to increase rather quickly. Remember, that's the idea of an exponential function. It doesn't increase at the same rate. As time goes on, it's going to increase or decrease rather quickly, especially if it's exponential growth, is what we have here. And then if we want to figure out, well, how long would it take for there to be 1 million bacteria? So after 6 hours, there's 15,000 bacteria approximately. So after how many hours would it reach 1 million? So at first you might think, man, it's going to be a long time. Well, it's actually about almost 10 hours is how long it would take. So from 6 hours, it'd be 15,000 bacteria. 4 hours later, it'd grow to be 1 million bacteria. And if you didn't get that answer, check your work with mine there so you can see where your mistake was. But hopefully that makes sense as far as how a geometric sequence works and how we can use what we learned in this chapter to be able to find some of those different values in these application problems.